Thank you everyone for joining this talk. Thank you for the organizer for the invitation. I'm very glad to be here to present this algorithm. This is a variant of one important algorithm in computer algebra. This algorithm was proposed by Mark van Hoeij to compute hypergeometric term solutions of Holonomic recurrence equations. When one sees this title, he may think that the subject looks complicated, but you will see during the presentation that these words actually represent some expressions that you already know. So now let's start. During this presentation, I will mention the following bibliography. The first one is a book by Wolfram Kopp on hypergeometric summation. This is actually an important reference for this talk. And then here we have the paper by Marco Petkošek. This was the first algorithm published for computing hypergeometric term solutions of Holonomic recurrence equations. And there is my thesis. This talk is a presentation of a particular part of my PhD thesis that I did under the supervision of Wolfram Kopp. And of course, we have here the original paper by Mark van Hoeij, where he presented his algorithm for the first time. This talk will follow this outline after an introduction where I will give some definitions and some background. We will go to present Petkovšek's algorithm briefly and mention some principle in computer algebra. Then we will move to the presentation of our approach with comparison to Mark van Hoeij algorithm. In this part, we will also show some live computation so that everyone can see how this algorithm works. And finally, we will conclude. So let us now introduce this presentation. Here are some identities. When one sees this, he may think on how to prove these. For example, the first one might seem quite easy because even from the combinatorial point of view, one can easily prove this one. For example, if you consider a set of n elements, then the left-hand side is counting the number of subsets with k element of that set. Whereas the right-hand side, as we know, this is the cardinality of the power set of that set. So these two represent the same thing and therefore can be identified. However, from the second identity, this is quite difficult to find because combinatorial identity does not give us a procedure to prove identity. So this one is quite more complicated. And here we have some power series identity. One may think at the first glance that this maybe it is from the well-known formula that we already have that the computer tried to generate such a right-hand side. But this is not the case. The algorithm actually takes the left-hand side and use some mathematical approach that we used to use when doing mathematics to find the right-hand side. And this talk is about one of the main ingredients behind such computations. And so the aim is to find a kind of general proof so that the computer can also prove such a problem, find the solution of such problems. The idea of the computations in hypergeometric summations come from the generalized hypergeometric series that can be defined as you can see here. Here we have the upper parameter B1 up to BP, and the lower parameter C1 up to CQ. And the programmer symbol is used. When you see B1K, the definition of such a term is given here. We call it factorial, shifted factorial or programmer symbol. This is the product of x times x plus 1 up to x plus k minus 1 when k is a positive integer and 1 when k is equal to 0. You can see from this definition a similarity with the definition of the factorial. So now to show the connection of the generalized hypergeometric series and summation and certain power series, here we give some few examples. You can see here that from these representations are correct, and this representation shows that all these right-hand sides can be represented with the generalized hypergeometric series. For example, if we consider 1 plus z power alpha, and once if we know that such a representation exists, then by this right-hand side here, we are able to immediately deduce the power series representation. Nevertheless, it is not by this approach that the algorithm works. what we just want to point out from these identities is that the generalized hypergeometric series may have a property that can be used to represent or to simplify the representation of the right-hand side that we have here and many more. So the main important property that we use from the generalized hypergeometric series is the fact that the ratio of two consecutive coefficients is a rational functions. When we say rational functions here is over a given field of characteristic 0. In general, that is what we consider. And here comes the definition of what we call a hypergeometric term. A term Sn is said to be hypergeometric over a given field K if the ratio term Sn plus 1 over Sn is rational. So this is a definition. And for example, if you consider factorial of n that everyone knows, factorial of n plus 1 over factorial n is n plus 1, which is a polynomial and therefore a hypergeometric term. So we know hypergeometric term is just the word that we use. Now that we have a hypergeometric term, we know that we are looking for a general procedure for computing some identities. And the first idea, algorithmic idea that was proposed in this purpose was given by Marie-Céline Fezenmeyer in her PhD thesis. She gave an algorithm that was used to prove some combinatorial identities. And from our first identity, we will show a little bit how these algorithms work. So let's consider Sn is equal to the sum from 0 to n of combination nk. This can also be seen as the summation over the whole set of integers of n combination k. This is because n combination k vanishes outside a finite set. We say that it has a finite support. This is for k greater than n, this is 0, and for k less than 0, this is also 0. This is some assumption that we use from the combinate by using this combination. So now Fezenmeyer approach use computer algebraic computations and find these well-known identities that we know for using the combinatorial term. So once Fezenmeyer's approach finds these identities, the algorithm sum now these identities over the whole set of integers. The left-hand side here will be Sn plus 1, and the right-hand side will be 2Sn. This is because these two terms actually represent the same, because by shifting the summation variable by a certain integer, this does not change the value of the sum. This is why here we have 2Sn, and therefore we got such a recurrence equation which is easy to solve, and we finally find Sn is equal to 2 power n. This is a proof, and the computer is able to do this. What people remark from Fezenmeyer approach is the fact that a recurrence equation of this form was always computed, and this was generalized, and we have this definition, what we call holonomic recurrence equation. That is a linear homogeneous recurrence equation with polynomial coefficients. This is a recurrence equation of order d, the d here for the highest order term. So note that together with d initial value, such a recurrence equation identifies uniquely a certain expression or a sequence. Fezenmeyer approach will be generalized and extended in a very clever way by Bertrand Teguia in the 1990s. And it is difficult to speak about computer algebra nowadays without mentioning the name of Zellweger, because his algorithm is really famous, as it was used to prove most of the hypergeometric identities that are known in these days. The idea of Zellweger's algorithm is, assume you have two sums and we want to prove that they are equal. Zellweger compute a recurrence equations for both sums and find a certain holonomic recurrence equations. If these two holonomic recurrence equations are the same, this happens often, then the algorithm checks the initial values, and if the initial values coincide again, then the two sums can be identified. This also applies for hypergeometric terms. Now, in the 1990s, people will work on holonomic recurrence equations by trying to compute the solutions of such a certain equations that will be polynomial, rational, and hypergeometric term. But note that a hypergeometric term by definitions, the family of hypergeometric term by definitions covers the family of polynomial and rationals. Observe that if you have an algorithm that computes holonomic recurrence equations at hand, this is Zellweger's algorithm, and another algorithm that computes the hypergeometric term solutions of holonomic recurrence equations, then we have a identities generator. This is because from a given sums, we are now able to find a hypergeometric term representations. This is also why from computing power series, we will be able to take an expression and easily generate what the power series of such an expression is. Two algorithms was proposed to compute hypergeometric term solutions of holonomic recurrence equations. The first one was by Petkošek in 1992. This algorithm, however, has a little issue with efficiency for certain type of holonomic recurrence equations. But a much more efficient algorithm will come up in 1999 by Mark van Hoeij. His algorithm computes a basis of hypergeometric term solutions and in a very efficient way. In Petkovšek's algorithm, this is not the case because the recurrence equation the output might be linearly dependent, and one has to use some other tools to make sure that the output becomes a basis. Mark van Hoeij implemented his algorithm himself in the computer algebra system Maple. And I will say that his algorithm is quite not straightforward for implementation in other systems. And this might be the reason why I think the only implementation of this algorithm that we have is available in the computer algebra system Maple. For Petkovšek's algorithm, however, we have an implementation in Mathematica and Maxima. Maxima is the software that I use to produce this algorithm that I'm presenting here. And we propose a kind of simplified version of Van Hoeij's algorithm that led us to a Maxima implementation with the same efficiency as Van Hoeij's algorithm. And, and our outputs are given in terms of factorial and programmer symbols. So this is what I'm going to present in this talk. So let us now move to the next part. Here, we are going to talk briefly about Petkovšek's algorithm. Petkovšek's algorithm, as we said, compute hypergeometric term solutions. And for recall, a hypergeometric term is a term whose ratio is a rational function. So we want to compute all such term solutions from these recurrence equations. Petkovšek's paper comes with two parts. In the first part, Petkovšek explains his algorithm named Poly for computing polynomial solutions. And another part, the main part of his paper, algorithm Hyper for computing hypergeometric term solutions. Algorithm Hyper uses algorithm Poly at some point of the algorithm. Let's now talk about algorithm Poly. Assume you have a recurrence equation like this one, and you want to find the polynomial solutions. If you know the degree of the polynomial solution, then you just have to substitute this recurrence term by that polynomial, and by equating the coefficients, you will finally get a linear system, and find the coefficients of that linear system will be computing the solutions actually. So what Petkovšek remark is that by computing a degree bound for polynomial solutions, the computation of polynomial solutions is quite easy to deduce. And I want to point out an observation that is quite clever from Petkovšek here. If you have such a polynomial and you substitute inside the recurrence equation, then we got something like this, relation 15. And by expanding this term here, n plus d power n, you observe that the coefficients of the expansion depend on the degrees by the binary theorem. So therefore, if we want to compute the degree bound n, it might be important to use these polynomial coefficients and some binomial expansion of this expression. Here can be n plus d minus 1 from n power n to n plus d power n. This is the idea of Petkovšek's algorithm Poly. I will not go into much detail, but I will just want to point out this principle of substituting something which is unknown inside the equations and get information about the solution. Now, Petkovšek's algorithm Hyper. Petkovšek's algorithm Hyper is based on the following lemma. This lemma gives a normal form representation of any rational functions. This is a kind of a version of what is also known as the Gosper representation of rational function. So any rational function can always be written as this one. We will not talk about the proof, we just use this representation. Such a representation is valid. The representation says that all the polynomial, that's a monic polynomial, A, B, C, and should satisfy these three properties. Here, the GCD means the greatest common divisor. Now, Petkovšek used this representation and write the recurrence equation for the ratio of a hypergeometric term. So the aim is to compute all the data in this representation of the ratio of a hypergeometric term. So by using the recurrence equation for the ratio of the hypergeometric term, Petkovšek proves that the candidates for an and bn must be monic factors of the leading, this is a trailing, and the leading polynomial coefficient. And this is why Petkovšek's algorithm is sometimes slow, because the computations here is exponential time on the degree of the leading and the trailing polynomial coefficients. So nevertheless, now if you have two candidates, an and bn, and we want to continue the algorithm, it remains to find z and c. First, we update the recurrence equations and write it for the polynomial c. And here to compute z, one only has to consider the leading polynomial coefficient of the Qi, and this will give a polynomial equation that can be solved to find the value of z. And finally, to compute the value of c, one has to use an algorithm that computes polynomial solutions of Holonomic recurrence equation. For that purpose, Petkovšek used his algorithm poly. An implementation of this algorithm is available in the computer algebra system Maxima with the command solverec. Note that Maxima is a free computer algebra system, so anyone can download it and try such computations. Here I show how to use this Maxima command. So you load the package, and you have this one. If we consider, for example, our first recurrence equation that was computed from Fesenmeyer approach, solverec command finds this solution immediately. And a second example here, this is the recurrence equation for the Fibonacci number. If we know it, this is 0, 1, 1, 2, 0, 1, 1, 2, 5, or 3. The sum of the previous numbers and get the other numbers. Then this is the computation of the Fibonacci numbers. This is the solutions. This is the linear combinations, as you can see. So the algorithm that was implemented in Maxima use some other tools to make sure that the output is the basis. Now let's talk about our approach and compare it to Mark van Hoeij's algorithm. First of all, as we mentioned earlier, this algorithm computes a basis of the subspace of hypergeometric term solutions. When you say a subspace, it's because a solution of a recurrence equation is a space, is in linear algebra, and this basis of hypergeometric term solution is a subspace, and we want this basis, and we compute it in an efficient way. The first thing we do is to consider a representation of a hypergeometric term. Any hypergeometric term can always be seen as the nth power of a certain constant times a rational function times some programmer symbol raised to some integers power. This gives also a representation for the ratio of a hypergeometric term. Note that such a representation is unique because we fix the theta k to belong to an interval of amplitude 1. Here we choose -1, 0. And you will see the advantage of taking such an interval later on. So the aim of the algorithm is to compute all these data. First, we start with the n plus theta k. Note that this n plus theta k power ek can be deduced from the ratio of a hypergeometric term. So the first thing we will consider is ratio of hypergeometric term, deduce the theta k and the ek, also the c, and therefore, and finally the value of r, which will lead us to this representation. We will do this from an example. We have implemented a Maxima code that generates recurrence equations from given hypergeometric terms. Here we have some hyper RE. This algorithm uses this. I give these two hypergeometric terms and I compute these recurrence equations. This is only done by linear algebra from the recurrence equation of both hypergeometric terms. Now we want to compute the solution. From Petkovšek's algorithm, we know that the monic factors of the leading and the trailing polynomial coefficients represent part of the hypergeometric term solutions. But since we are considering Pohammer symbol with the theta k in an interval of amplitude 1, we will only consider monic factor modulo z, so that this means n plus 1 and n plus 2 actually represent the same monic factor modulo z, since, for example, the root of this term here is -1, and without considering the multiplicity, and here we have -2. But these two, but the difference is an integer, then these two can be considered together. This is why here we have n plus 1 power e, and here we want n plus 1 square for the trailing polynomial coefficient. Now, there is another step that we consider to take the exponents of these polynomial coefficients. Observe that in Petkovšek's algorithm, this is much more, there are much more terms to be considered. This will be 4 times 5, this is 20, and then times the 3 here, which is 60. 60 computations to be done with Petkovšek's algorithm. Whereas with Van Hoeij's algorithm, already at this step we can observe that there is a gain of efficiency. Note that we are considering, first of all, polynomial over the rational field. Now, one consideration from Van Hoeij's original algorithm is what he called valuation growth. This is something that he used by computing left and right solution and defining what he called finite singularities. What he called finite singularities is actually what we consider here as monic factor modulo z, and this represents actually the same. Our approach is to say that the computation given by Van Hoeij, where he used valuation growth, are actually the same that we do by only computing the ratio of the monic factors of the leading and the trailing polynomial coefficients. And here, the highest exponent to be considered appear as the sum of the power. This is why the 3 plus 4 here, which gives 7, as considered. And the minimum appearing degree of a given singularity point, which is here 1, -1, will be 3. So there is no need to consider, for example, n plus 1 power 2 for the leading polynomial coefficients. This is what we consider here, and then we have this possible ratio of the Pohammer parts of hypergeometric term solutions. The next step in this algorithm is to use what we call a local type of a hypergeometric term. For a definition, this can be seen as the unique triple nu CB that characterizes the asymptotic expansion of order 2 of the ratio of a given hypergeometric term. So from this now theorem that was given by Van Hoeij in his paper, we have a connection between the representation of a hypergeometric term and a given and his local type. Note the EK, the degree. This is the difference of the degree of the numerator and the denominator of the rational function in the representation. And then here the theta k and the EK. So now how do we compute local type of hypergeometric term? From a given ratio of, from a given rational function, this is quite easy, because once you have the degree of that rational function that we can find easily, for example, for 1 over n plus 1 power 5, the degree is -5. You take the opposite and you add 1. You take the Taylor expansion, and then this -1 here will be the value of b, and u will be that -5. This is how it is computed from a given rational function. The most important part of this step is the fact that we can compute local types of hypergeometric term solutions directly from the recurrence equations, in such a way that if such local types do not exist, then we can say in an affirmative way that there is no hypergeometric term solution of the given recurrence equation. The approach used by Van Hoeij in this step is what we call the Newton polygon algorithm. This uses some coefficients of the polynomial equations and the valuations of the coefficients. So, but we use only asymptotic computations. This is by considering the recurrence equations for the ratio of hypergeometric term solutions. The idea is similar to what Petkošek did for his algorithm poly. As you can see here, when we substitute this asymptotic expansion of order 1 in the recurrence equation, and by computations at infinity, we observe some formula for the value of C and nu, similar as Petkovšek found for the degree bound of polynomial solutions. So we come up with a theorem that this may look quite complicated, but the formula are really simple. To compute the value of nu, one only has to consider the degree of the polynomial coefficients and their position, and deduce the value of C by computing a polynomial, solutions of a given polynomial equations. Here, the coefficients are taken from the leading polynomial coefficients of the polynomial used in formula 25. And finally, to find the value of B, this value found for C and nu are used so that now this representation of the rational function is used inside the equation, and the value of B is found in a similar way. This will be also a polynomial. So now, assume we already have the value for C, nu, and B, and then we have all the possible local type of hypergeometric term solutions. Let's apply this from our example. We collect the coefficients of the polynomial coefficient of our recurrence equations. This is done by the recov command that we implemented. This collects the polynomial coefficients, and now this is a maxima command. This will expand the polynomial coefficients. This is now saved in the variable cof re. Then we use the cof re is now used, and you compute the local type. Our algorithm to compute local type is local type, and this will give these two possible local type of hypergeometric term solutions. This says that we have at most two solutions, two hypergeometric term solutions in the basis of hypergeometric term solutions. And from the ratio of the programmer part of hypergeometric term solutions, there are only two candidates that remains, because these two are the only one which match with this computed local type. As you can see, this is already close to the answer of the result of the computations. The last step is to compute the rational function Rn. From Fuchs relation, we have already this formula. And since from our previous computation, the value of this sum and the value of this B are already known, we can easily deduce the value of the difference of the degree of the numerator and the denominator of Rn. Now, if we have such a degree, what we do to compute now the rational function is that we compute what we call a universal denominator. A universal denominator of if you have a recurrence equation and you want to find rational solutions of that recurrence equation, there is a step that we usually consider in computer algebra, that is the computation of the universal denominator. This is a denominator which is multiple of all polynomial solutions of that recurrence equation. You can see this as a black box. Now that suppose now that we have computed that un, it remains only to deduce n by solving a linear system. This is because the degree bound for this n can be deduced since we already have the difference of this degree. And since we will have the degree of u, the degree of n will be easily deduced, and now it will remain to solve the linear system. This is where Petkovšek's and Van Hoeij's original algorithm ends. At this step, he will only his algorithm replace the output, like we can see here. This 1 over n plus 1 square will be gamma n plus 1. So there's no other computation. But in our algorithm, we consider another step in order to write the output in a certain nice way. This is what we call a simple formula. The aim is to write the output in a way that it looks more closely to what we usually see from the mathematical dictionary. So we want to write the output with integer linear arguments, or if not possible, with programmer symbol. And this is very important when computing power series because the initial value can easily be checked. This is done in this way. The computations are quite simple. If you know how to manipulate the factorial or programmer symbol, then you easily deduce that when you have the ratio xn over yn, where x and y are constant, whose difference is an integer, then this can be written as this one. And this is a rational function, a good simplification. If you have a programmer symbol of an integer, then you can easily write it as the ratio of two factorial terms. And note that the k here cannot be a non-positive integer in our approach. And this is where the use of the amplitude, the interval of amplitude 1, that was -1, 0, the advantage of using that interval is can be seen here, because k minus 1 can never be negative. And this is very important when we compute the representation with hypergeometric terms. And you will see in the live computations how the representation that our algorithm gives can quite nice. So with a rational function with denominator 2 now, we have such a representation. This can easily be proved, just a manipulation of the product of terms. And note that this substitution procedure is the aim is to compute the product of a certain rational function starting from k equals 0 to k equal n, to k equal n minus 1. But we, in our approach, the algorithm consider a rational function written in a certain way. We also do not want a rational term to be negative appearing in the computation, because sometimes it is not also nice. So that is the algorithm. And for the computation of the hypergeometric term representation, you may recognize this one. This is the coefficient of the power series of the cosine function. And this was computed from the ratio of hypergeometric term taken from the recurrence equation of that power series. And all this comes from such a computations from power series. So we implemented this algorithm of pour factor simple. Now, in a nutshell, this is how the algorithm works. In the first step, we compute a set of ratio of Monic factors taken from the leading and trailing polynomial coefficients in a way that what is called variation row in Van Hoeij's algorithm are computed in a different way by considering the respective minimum appearing degrees from the leading polynomial coefficients or the trailing one. In the second step, we use asymptotic computations to compute what is called the local type of hypergeometric term solutions. This allows us to filter again considerably filter the set of ratio computed in the first step, and also have information about the rational function R in the representation. And then in the last step, we compute the universal denominator UN for the rational function R and deduce N by solving a linear system. And finally, write the output in terms of simple formulas. This is written the output using factorial and programmer symbol instead of gamma representation. Now, applying our algorithm, we implemented this in Maxima as Hyper Van Hoeij. And if we apply it from our given recurrence equations, you can see that the output is the same basis that we use to compute the recurrence equation. Whereas these two approaches, the computation of recurrence equation and the computation of the solutions are very different. So you can see that this algorithm works as a reverse process. Now let us do more computations. So I will launch Maxima and show you how to use this algorithm. What's happening? Okay, sorry, there's a visual. So I open Maxima now. Here I load the package. This is the full package of my PhD thesis, but I will only use a particular part of this package. I load the package. Now I load the Maxima solve command. First, I consider three hypergeometric terms. This is h1 factorial n. The second one is n plus 1 over factorial n plus 1. And the third one is h3. This is represented with Pochamer symbol, half n and one-third n squared. This show time command will show the timing of the computations. Now, we compute the recurrence equation with our algorithm sum hyper RE from these three hypergeometric terms. We find this recurrence equation quite big. And then we use the solve-rect maxima command to compute the solutions. Maxima will find this, and this is the timing that maxima used. Observe the square root of pi, and this kind of term that we don't want really when we are doing computations. And these are coming from the use of the gamma representation. In fact, this term was computed from this ratio, because we have also implemented Petkovšek's algorithm just to compute the ratio of hypergeometric term solutions directly from the recurrence equation. And you can see the timing here. Now let's use our implementation, our variant of Van Hoeij's algorithm. Just look the timing and you will see that this is 10 times faster than this one. But this is just a simple example. Let's consider something little more complicated. As we said, if the degree of the leading and trailing polynomial coefficients are high, the timing increase depending on the degree of the leading and the trailing polynomial coefficients. So here we consider another recurrence equation, even though the recurrence is not big. But the solve-rect command, you will see that the timing will increase for the computation. This is already 178 seconds, whereas here it was 0.96. And using the approach by Van Hoeij, this is immediately computed. So now this is the part where I will really check the efficiency so that everyone can see that Van Hoeij's algorithm is really efficient. I consider the power 5 here and power 3. And in H2, also with higher order term, the recurrence equation is quite big. This is why I use the dollar here, and I will not show it. I compute the recurrence equation. Then I will launch the computation using the solve-rect command. At this step, I will run this computation and go back to the presentation. I will conclude, and you will come and see the result before saying thank you. So I run this. And I go back to my presentation. And yes, so we have implemented an algorithm in computer algebra that implement Van Hoeij's algorithm in a different way and accomplish the same efficiency. And you can download my code. This code is free. You can download it from my web page here as hypergeometricterm.map. This is a link. And if you have any question concerning this algorithm, you can contact me. This talk was also presented in the International Congress of Mathematical Software. This was 2 weeks ago. And I did a similar presentation for presenting this algorithm. Note that for use, when you want a solution of an extension field of the rational field, you must specify a third argument here, C. This is so because we realize that in many cases, the hypergeometric terms that we are usually looking for do not need some extension field. So that is why at this step, we implemented 2 different algorithms for the 2 kind of computations. Petkovšek's and Van Hoeij's algorithm cannot compute some other generalization of hypergeometric term. And this was given in my PhD thesis. This is the most important part. And if you want to know more about this, you can see my PhD thesis. And you will see that, this kind of computation can be generalized, and and for example, for power series, you can see that these are really important even for asymptotic series. So let's go back to the computation and see. I think it's finished. So it was 1 minute and something. And here we have p power 5. This is not good and we don't want it. Now let's use our implementation of Van Hoeij's algorithm. You will see that this is almost a second, less than a second, the same computation in less than a second. So you can see the advantage of using such an algorithm. So as a bonus, I want to show some power series computations. Here, this is the square root of 1 plus z plus 1 over, this was given in the introduction. The power series computing is this one. And this is immediately, the intermediate steps in this algorithm are the following. We compute a differential equations from a given expression. This is what is also called the holonomic differential equations. And from this differential equation, we deduce a recurrence equation. When you're using Hyper Van Hoeij, we compute the hypergeometric term solutions. We check the initial values and we find this power series representation. So the computer actually proved that the power series of this one is this one. If you use Maple, for example, this is known as the best computer algebra system for mathematical research. So we bring the same package used for power series computation. And you will see the difference in the power series representation. Here we have the square root of pi and 1 minus 1 power n. And sometimes this can implies that can make the algorithm miss some computations because it is difficult to check the initial value when such a term are considered in the initial in the power series representation. So that is the full talk, I think. And then I will say thank you. So do not look too much my smile here. I just want to draw attention to the t-shirt that I actually wear to show this result that I like very much. This is a picture of the computation of M-fold hypergeometric term. Thank you for your attention. Thank you for listening.